All right. Hey, everyone. So I've been working recently on resource-guided program synthesis. So in general, synthesis considers the problem of turning some high-level declarative specification into an executable program. So for example, we might want the synthesizer to find a function that returns the intersection of two lists. We might give the synthesizer a formal spec or maybe just some examples, but in either case, we'd expect to get something like the recursive function I showed you here. More concretely, the Synquid synthesizer generates code from refinement type signatures. So here we have the refinement type for common, a function that takes two sorted lists and returns a list containing their intersection. To indicate that the input lists are sorted, we have defined this xlist type, and then common outputs a list, which we've annotated with an assertion that the elements in the list are in the intersection of the elements in the input lists. So the synthesizer also needs a set of components from which to generate code. Here we're just going to give the synthesizer some logical predicates, some type constructors, and then this member function, which tells you whether or not a given element is in a list. So the functional spec and the set of components make up a synthesis problem. In this case, Synquid outputs this implementation of common, which is recursive, it's concise, and it's provably correct, which is exactly what we wanted. So the problem here, which an experienced programmer might notice, is that common runs in quadratic time. It traverses through the first list and calls member every time, searching the entire second list every time. However, it is possible to use the fact that the input lists are sorted and write a linear time implementation that never calls member. The implementation here iterates through both lists simultaneously, comparing the heads of the lists in order to figure out whether or not it could possibly be in the intersection. So ideally, Synquid would somehow be able to reason about the algorithm's performance and find faster implementations like this one whenever possible. This is much longer, right? And all modern synthesizers basically just return the first program they find that meets the spec, since they're searching such a huge space of programs and have no way to differentiate between functionally correct implementations. So this is a general problem in synthesis. If it's ever going to be realistic, we need to somehow integrate resource analysis into the synthesis procedure. As we all know, programmers are concerned with much more than just correctness as you write code. You're constantly thinking about runtime or memory usage or some other resource metric. So my work here is going to focus on integrating this resource analysis into the synthesis process so that we can generate efficient programs. So I focused on Synquid earlier because it turns out that we can use Synquid as a framework for type-directed program synthesis by developing type systems that fit within its round-trip type checking paradigm. So if I can develop a type system for resource analysis that fits this framework, we can use resources to guide the synthesis process. So luckily, this community has done a lot of work on resource types, and we can take inspiration from that. So to this end, I've developed RE², an affine type system with refinements and resource annotations. So I don't really have time to go into detail about how we reduce resource analysis to a constraint-solving problem. So instead, I'm just going to show you how we specify resource semantics and resource bounds in order to guide the synthesizer to find implementations that use only the allotted amount of resources. So we'll start with the exact same type signature for common I showed you before. And then we'll add some information about its resource usage. It's worth noting that this technique is inspired by automatic amortized resource analysis, but we needed to extend it with polymorphism and dependent resource annotations in order to effectively specify synthesis problems. So first we need some kind of model of our resource semantics. So here we put a 1 on the function arrow on common to indicate that a recursive call to common incurs a single unit of cost. In general, the type system is parametric with respect to the resource in question. You can annotate different function signatures in order to count whatever resource you might be concerned with. But here we're just going to keep it simple and look at recursive function calls. So we also have to give the synthesizer an upper bound on resource usage. So here we annotate each type variable with a 1. This basically means that every element in both input lists can be used to pay for a recursive call. We want the synthesizer to try to find a linear time implementation, and this means that we can make at most 1 recursive call per element in each input list. So now we have a complete specification for ReSyn, the synthesizer I've implemented using the type system I developed. And ReSyn uses resource analysis throughout the synthesis process, modularly verifying resources in order to prune away slow programs as early as possible. So we can give ReSyn the functional specification, the set of components, and now our resource information. And ReSyn generates the exact linear time implementation of common I showed you earlier. So it's worth noting that ReSyn has a couple other features. We can verify fine-grained resource bounds that depend on functional properties. And we can also verify and synthesize constant time functions for those of you who are concerned about security and want your code to be resistant to timing channel attacks. So anyways, you've seen a bit about what the tool can do. I think there's a lot of exciting work to come in this area. Thank you for listening.
Then, if anybody has any questions, please type them in. So I had a couple of questions while watching your presentation. One is, you started with Synquid, which is one type-directed program synthesis engine, and integrated resource analysis onto it. Could the same kind of approach be used in other kind of type-directed synthesis techniques that maybe don't use refinements as heavily?
But yeah, it is definitely applicable to other type-directed systems. The advantage of using the refinement types is that we can then use program expressions in our resource bounds, and we can verify, or yes, yeah, that's it. We can use program expressions.
Another question that comes to mind is reasoning about performance bounds becomes even harder in a language with lazy evaluation. Have you thought about whether the similar kinds of techniques might apply to that kind of setting as well?
Yeah, I agree that sounds much harder. I'm not ready to try to model Haskell's lazy semantics with this system, but it might be possible. I'd love to talk about that later.
Next year. And then one more question about the kinds of polynomials or other kinds of bounds you can currently reason about, and what kind of limitations you might see going forward.
So right now, I've only implemented linear bounds, but I think polynomials are absolutely possible. Again, kind of following the techniques from this automatic amortized resource analysis. And then beyond that, logarithms also potentially possible if we axiommatize it, but that's less well thought out from my perspective. It's future work for sure.
So one question from the audience is, in your benchmarking so far, are there examples of algorithms that can be synthesized now but couldn't be synthesized in prior versions of the tool?
Of programs that can be synthesized now? No, I don't think so. I think we have the exact same functional expressiveness as Synquid did before. One advantage now is that you may not have to annotate these termination metrics and show terminations, so it does kind of help the user in that sense by not forcing them to manually prove termination, basically.
The example that you showed was nice, where the input lists were already sorted. In a setting where the inputs were not already sorted, do you think that ReSyn would be able to synthesize an efficient algorithm even if the inputs weren't sorted?
Well, I don't think there is a more efficient algorithm than the naive quadratic approach in that case. Well, will that be faster? I guess you'd have to do logarithms in that case. No, not right now.
Okay, and then maybe one last question. So does your type system verify the resource usage annotated on functions, or must they be correct by construction? Are they trusted?
So yeah, we can verify functions against a resource bound, or you can just annotate. You can just provide a type signature as you might in a library.
Okay, great. Thanks a lot, Tristan. Let's thank Tristan again.